his job is bridging the gap between the customer and Nichia's product research and development. This is sometimes they speak really different languages, and this is then your job to do that. And he has worked as an optical measurement specialist at a scientific and British certification laboratory before, so you know what you talk for. Very good, and we look forward to your presentation exploring the challenges in micro-pixelated light sources, and the rest is from you. Thank you.
Thank you, Wolfgang, for those very kind words. Yes, it's quite a title. So today we want to share with you the developments and especially some of the challenges in the development of our micro PLS. Unfortunately, the micro has changed to an M there. That should be the Omicron symbol. You'll see it later on. But development of light sources, I think it has been said before as well, is not a solution in itself. It needs to be considered in the environment. We are not a company just to provide a light source. It's an industry. So how does micro PLS and micro pixelated light sources fall into our vision and mission? I will briefly talk about, and I will guide you a little bit through automotive device history of Nichia as well. After which I will then place the micro-pixelated light source in our portfolio. And then we get to the meat of the slides of the presentation of today. And I will highlight some of the required collaboration technology that has gone into the development of our product. And then some of the details of our pixelated light source and the challenges that we had to face in the development. And of course, some last minutes to conclude the slides. So Nichia is part of the environment of automotive lighting, and we have to consider everything. As a light source manufacturer, we are one of the first to be asked to consider the environment. We have to make very efficient light sources. But not just efficient light sources, we have to think about how can our light sources help impact safety. And as a light source, we are there for visibility. So of course, visibility is always in the back of our mind. And for us, it's really important that we look to the light creation with our partners and our customers to bring comfort and a safer society. So where has Nichia come from in the automotive device history? Of course, we have the introduction of the first blue LED in 1993. At that time, it was definitely not ready for automotive lighting. But in 1998, we had the first introduction, the launch of the first automotive white LED. You can see it's not a headlamp application LED, as you can probably imagine. Regulations back then were slightly different than they are now, and the regulations were definitely not ready for LED. But luckily, shortly after, in 2007, just a mere 9 years later, the first LED for automotive low beam was developed. And again, you'll see this looks nothing like any of the LEDs you'll see in cars nowadays, because this LED was still ahead of regulations. Then, 2 years later, the automotive ceramic LEDs were developed. And that's then where also regulations started to catch up. And then a few years later, we see the launch of scalable chip scale LEDs. And these are, and that's what Benno has shown as well, these are the LEDs that are now in 80% of the use cases for automotive lighting, especially for exterior and headlamps. Of course, 2017 we had also wide laser diodes for automotive, and then in 2020 we started the R&D of our micro pixelated light source, which we call micro PLS, which is micro pixelated light source, which is the integration of an ASIC and micro LED, and it is a full integration. So ASIC and the LEDs are together, there's no separation there. So how does our micro PLS fit in our portfolio? You can see our automotive portfolio here, and one thing you'll notice is that it's not just LEDs. So we also have some magnetic materials and cathode materials for battery, where we are active in the automotive industry. But of course here, exterior is where a micropixelated light source fits in. So we make room in our portfolio for our new device, for micro PLS. Collaboration technology. We are an LED company. We are not an electronics company. We know InGaN, but silicon is a completely different beast. So we need to work together with a partner. And that's where that collaboration comes in. So what we have done at Nichia is we have developed the micro LED and further developed the micro LED to be ready for our micropixelated light source. So what we have achieved is a 50 micron pitch micro LED with 70 candela per square millimeter or 70 meganits, white colored light, which is made up of, as usual, our blue InGaN and then a phosphor converter on top. And what you can see here is a cross-section of a single pixel. So at the top, as I mentioned, we have the chip itself and the converter, and below that directly is the silicon of the ASIC driver. So there are no external electronic drivers necessary. The PWM engines are on board. The linear PWM engines are directly below the LEDs. So the ASIC consists of several functions, or it has several functions. As I mentioned, the primary function I would say is the onboard PWM engine. Without the PWM engine, it's not possible to dim or make complicated light distributions like you can see here, a low beam distribution. So the PWM engine is really the engine of the ASIC. Of course, you have to send a signal somehow to the device, and for that we have several video interfaces to send the video stream, and of course control interfaces to be able to read out and register the state of the device. Additionally, we have an integrated EEPROM control for reading and writing to the EEPROM, so it's not necessary to have an additional EEPROM channel going there. And very important, diagnosis and monitor functions. So for such a device, as you can imagine, if this is for a headlamp application, it will be running a lot of power, and it's a very small chip, which means that it will run very warm. Yes, LEDs don't produce heat, but I think that myth has been solved already or thrown out the window many years ago. So there's a lot of heat produced in this device. And LEDs are very sensitive to heat, so correct control of the temperature is very important. So inside the LES, inside the light emitting surface, we actually have 16 temperature sensors. So not just outside or near it, no, actually in the silicon we have implemented several junction temperature chips. And then it is bringing the micro LED and the ASIC together into a single package. So what you see here is an SMD package. So it's able to be produced and mounted in standard SMD assembly machines. And everything is in there. So there's a few electrical connections that you need to make, but there's no ancillary electronics required. And of course, what this does enable is sensor fusion with intelligent lighting. So of course, messaging is possible. And just to reiterate, these are Photoshop images. These are not, nor are these. So glare-free ADB is of course very possible with 16,000 pixels. And lane assist and pedestrian crossings, even symbol projection is possible with our light source. If we have then a look at some of the details of micro PLS technology and what are the technologies that are required. As I mentioned, micro LED technology, you can see here we have 16,000 pixels and it's individual pixels. That's why we call it actually micro LED technology. They're individual pixels that are all not separately placed, but they have a physical separation between each other. I also highlighted already the ASIC technology, so bringing those two together is the first step. Of course, then the converter technology, so we have to minimize the thickness, but still have the right color homogeneity and light homogeneity. But just that doesn't help the tier 1s or the OEMs because it still needs to be packaged. So we have interconnections and so we have the interconnections from the ASIC going to the substrate, which is actually the material that is the solderable part of the product. And to cover those interconnections, it's filled with a resin material, which we have optimized for unwanted stray light. And then of course it is very important to be able to comply with regulations, so we have compliance with ACQ 100 for the ASIC and 102 for the package overall. So we talk about a bright 16K pixel array, but that wasn't always the case. When we started the development, and you saw already 2020, that's when we actually had our first prototype. Before that we were already working on it on paper. Our first prototype was around 20 to 30 candela per square millimeter. So we knew we had a big challenge ahead of us, a large mountain to climb, because that was not what the market demanded. The market's demands was a minimum of 70 candela per square millimeter. So there was a few hurdles to climb, and in 2022, or end of 2020, we were close, we were at 60 candela per square millimeter, and then last year we did manage to climb the 70 candela per square millimeter luminance hill, but we don't stop there. So we already have achieved a higher luminance than we set out to achieve. But with a large area source, and especially with the resin filling at the border, we know that stray light is a risk for a product such as this. So we knew we had to look into this. And that is what we have done. We have looked at many materials, we have talked to our partners, how can we minimize this unwanted stray light. And what you see here is a luminance image, basically a zoom in of this bottom part here, where here you have a cross section with showing the relative luminance. And this is the secondary reflection peak caused by the silicon border. So that is critical to minimize. And with our material experts, we have settled now on our final design for the current product, where we have managed to minimize the stray light. I also mentioned already thermal performance. This device will use somewhere between 10 and 40 watts. And we're talking about an effective light emitting size of tens of square millimeters. So it is I would invite you to come to our booth to have a look at the actual product. You'll see how small it is. If you then imagine pushing, let's say 30 watts through this device, you can imagine how critical thermal management is. And again, Benno, you highlighted it before. I think thermal management will be a game changer, not just for micro LEDs, but also for other solutions in the future. How can the tier ones, the OEMs, and how can we as light source suppliers make sure that is as less of a challenge as it is currently. So we do realize that the thermal resistance of such a device is a critical parameter. And the other thing that we quickly realized is, of course, that a device with 16,000 individual junctions doesn't have a single thermal resistance value. So what we have seen is that if we still want to quantify the thermal resistance as one number, it will be a light pattern dependent value. So what we at least have achieved is that we have an RTH less than 1 Kelvin per watt with a homogeneous light distribution. So in 2020 we were at around 0.8 Kelvin per watt. Earlier this year, we managed to reduce that even to 0.7. For light distributions that are slightly more focused, so more for application cases, you'll notice that the thermal resistance or the effective thermal resistance seems to be a little bit higher. But that's again a part of the product and is not a specific challenge for our device, but for all large area light emitting sources with individual LEDs. And of course robustness. Because this device is an automotive device, if it isn't automotive qualified, no one will design it into their car. Which was a challenge because there was not yet an in-vehicle reliability test standard for a micropixelated projection device. So we did a lot of tests with our partners, and we talked with them what would they need to convince their customers to be able to allow them to put such a device in the car. Of course, the first look is to ACQ, and there the ASIC part has an ACQ 100 qualification, and the device as a whole has an ACQ 102 qualification. And of course, for us as Nietzsche, quality is of highest importance. So all our devices undergo a full end-of-line test, a full ASIC functionality. We have checked for contamination and foreign substances. And we made sure that the handling of the device, as I mentioned, it's a solderable SMD package, is as convenient as can be. And we have seen in our tests and with our partners, we have seen that the design that we have has a very high durability against solder cracks. That is to say, we have not seen any solder cracks. Thank you, Wolfgang. That brings me to my last slide. Okay. So perfect timing. We will always continuously improve our light sources. So Kaizen is a Japanese term for continuous improvement. So please watch this space, as they say. This is not the last you will see from Nietzsche on micropixelated light sources. We face our challenges with a technical mindset, and we love to contribute to the automotive future digital lighting world. Thank you very much for your attention, and I also want to thank my colleagues for the work in Japan on this device.